Hello, welcome back to Dinosaurs. We're going to keep going through Module 2. We talked last time about life before the dinosaurs, so things that happened back in the Paleozoic when life first started establishing itself on land. First, probably plants, very basic plants, fungi, lichen, then insects, and then finally the tetrapods, the 4-foot vertebrates, climb up on land. Now we're going to talk about the Mesozoic world. We're going to talk a lot about the creatures next week. So I want to kind of set the stage with what's going on with the climate and what's going on with the continents and the oceans and what the world looks like. Then we'll talk about some of the life next week. Then we'll get into some more concepts of dinosaurs. So dinosaurs are coming. Just be patient. By the time you're done with this class, you're going to be sick of dinosaurs, so you'll remember this fondly. Before we get into that, though, some announcements. So again, welcome to Module 2. Okay. All right, so let's talk about what we talked about last time. So we talked about life before the dinosaurs. So the big question here is, why did life leave the oceans and expand onto the continents? Life developed in the oceans, probably initially about like 3.5, 3.8, maybe as long as 4 billion years ago. But it didn't really crawl up on land until much later than that, like 400-ish million years ago. And that was very basic, very primitive. Life developed in the water and stayed there for a very long time. Why did it come back onto the continents? So I'll give you a second to think. And there's some funny cartoons there to pass the time. Ha ha ha, very, very hilarious. And the answer is, so basically untapped opportunity. The land was essentially barren. There were plants, there were insects, there were some things on the land, and there were food sources. There was very little to no competition, no predators yet. So it was a good opportunity to go stop competing for everything. Is life on land easier? No, there's many ways that life on land is harder. For one, water supports your body weight for you, and you don't need to lug yourself around on your limbs. A lot of people raise some really good points in the discussion board about how in some cases life on land is actually harder. There's a lot more extreme temperature swings. The oceans are a lot more uniform. It's just kind of in general a little bit more, at least predictable, not necessarily safer, but predictable in the oceans. Were organisms better adapted for land? No, they'd had 4 billion years of evolution, 3 billion years of evolution for living in the water. Just felt like that. Pretty much that's not the answer to anything. There's always a reason. What that reason is might be a little tricky, but there's a reason organisms crawled up on land, and it was to find these untapped opportunities and start exploiting them. And then it was a little bit of a land rush and an arms race. What was the major advantage of the amniotic egg? So this was a big landmark in the evolution of terrestrial land-based species. What was the main advantage? All right, the main advantage was that it freed animals from the water's edge. So fish, amphibians, even amphibians live on land, they live out of the water frequently, but to reproduce, they have to go back to the water to lay their eggs. Amphibian eggs dry out very quickly on dry land. Fish eggs do not survive on dry land. Things like sea turtles, snakes, they lay eggs, they lay amniotic eggs, and it's essentially like a little suitcase of seawater that they can carry with them further inland. And it allowed organisms to move away from the water edge and into the continental interior. Again, why? Opening up new opportunities, opening up new niches, opening up new space, less competition initially, but again, that spurs a big land rush and another arms race between predator and prey. So can they make more of them? No, they're a lot more energy intensive. Organisms generally have much less of them. Think about how many eggs a fish lays versus how many eggs a bird lays. Less supervision or tending. Fish generally don't tend their eggs at all. Some do, but most just kind of leave them. And then like egg-laying reptiles, for example, tend the nests pretty well. That kind of varies, but more intensely than that anyways. Okay, so where, or I guess better to say is when were we? So where did we leave off? So The last thing that we talked about last time was the Great Dying, this massive mass extinction, the largest mass extinction, the greatest mass extinction, well, maybe not greatest, the worst mass extinction in all of recorded history, the worst mass extinction that ever happened. The one at the end of the Cretaceous that killed off the dinosaurs gets all the publicity, but the one at the end of the Permian was much bigger. We've also assembled Pangaea. This supercontinent of Pangaea is together. All of the continental landmass of Earth is smushed together into this one continent, Pangaea, all Earth. And the early Mesozoic, when dinosaurs first come on the scene, sort of sees a reversal of both of those trends. We start with a supercontinent through the course of the Mesozoic, the time period that the dinosaurs lived. So here's again the geologic time scale: Cambrian, Ordovician, Silurian, Devonian, Carboniferous, Permian, Triassic, Jurassic, Cretaceous, Cenozoic. I'm not sure why that's Cenozoic, not Neogene, Paleogene, and Tertiary or Quaternary, but this is what we're talking about. This is when the dinosaurs lived. This is the time period that we're going to be speaking about for the rest of the class, from 252 million years ago to 666 million years ago, starting with the Triassic, moving into the Jurassic, moving into the Cretaceous. There's this big, so again, this is number of genre on Earth. We see the Cambrian explosion, the Ordovician radiation, some little kickbacks with mass extinctions, but then life rebounds quickly. Another mass extinction, life rebounds quickly, kind of levels off here as things are exploring into the continents, and then it falls off a cliff at the end of the Permian. This is the Great Dying. We rebound a little bit of a cliff at the Triassic. We'll talk about that later. This is really what kind of creates room for the dinosaurs to get more diverse and bigger. And then we just see this massive expansion in biodiversity, the golden age of the dinosaurs, and then the Chicxulub impact at the end of the Cretaceous, and then another big boom of diversity into what we see today. There's a little bit of a skew in the fossil record, but today is probably the most biodiverse the planet has ever been. There's just more niches, more variability. We might talk a little bit about why later on in the class, but definitely cover it in paleontology. But the Earth has never been more biodiverse than it is today. Well, actually, probably more like 100 years ago or so, before we started maybe sliding off another cliff. Let's talk about what the Mesozoic was like. Let's kind of go back in time and what would it feel like to be in the Mesozoic between 252 and 66 million years ago? What was life like on Pangaea and further? So first, let's talk about the climate. What was the climate like in the Mesozoic? So this is a thread that somebody posted in the discussion board, a very interesting and good topic. I think they actually asked about the Permian, but it's a good question to ask. What was the climate like? Well, the answer is that the climate was quite variable. So remember that the Mesozoic goes from 252 to 66 million years ago. That's 186 million years of geologic time. That's a lot of geologic time. The dinosaurs have only been extinct for 66 million years ago. So it's like 3 times longer than since the dinosaurs have been gone. So it's a very long time. And over that time, the climate wasn't always the same. There were changes, and we'll talk about those changes in just a second. But one constant is that it was warmer than today. At times, it was much warmer than today, and it was probably always ice-free, or at least large continental land ice sheet free. There wasn't widespread glaciation. Some of the higher altitudes, more towards the poles, probably had isolated valley glaciers, but there's no evidence for widespread glaciation. The Earth was essentially ice sheet free. But one thing that often gets a little bit overlooked is that there were still seasons and there were still different land masses. Well, Pangaea was a very large landmass that actually stretched from pole to pole, but we still have the same seasons that we have today. We still have the same latitudinal variations that we have today, where it's hotter at the equator and cooler at the poles. As climate's warmer, those differences kind of get a little bit smaller, but it still exists. And so we often think about the Mesozoic climate as like this really hot, steamy, rainforesty, lots of water around. There's always the ubiquitous volcano in the background. Volcanoes were not necessarily any more common then than they were now. So not sure why people always show volcanoes with dinosaurs, but as you can see, it's a pretty common theme. And yeah, some parts of the Mesozoic in some places at some times, it was like this. It was steamy and rainforesty, but in other places it was more temperate. And there was fall in the Mesozoic. There was winter in the Mesozoic. There were polar land masses during the Mesozoic that actually got quite cold. There's a little bit of debate about how dinosaurs would have interacted with the cold, but there's pretty strong evidence that dinosaurs lived and in very cold climates on the continents of Australia and Antarctica when they're still very polar. Australia sort of creeped its way a bit north, but dinosaurs probably tromped around in the snow at least a little bit. How can a cold-blooded animal highly function in such an environment? Well, maybe they weren't so cold-blooded after all. We'll talk about that a little bit later in the class. But when you think about the Mesozoic climate, remember that it's highly variable both in time and in space, just as it is today. The Mesozoic climate is not just one thing. So while we're having a natural science gen ed course discussion, one of the things I'd like you to take away from this course is some basic understanding of climate, because obviously it's one of the leading issues that's facing us today. So I just want to spend a little bit of time on that before we move on. So one of the big misunderstandings that people have about climate change is the difference between climate and weather. If you can't discriminate between weather and climate, then the discussions get really complicated really quickly. So weather is local and it's short term. I'm looking out the window right now. Oh my gosh, it's actually sunny out. That's weather. It's short term. Tomorrow it might be 20 below and snowing. That's weather. Climate is regional and it's long term. It's kind of the average atmospheric conditions. So this cartoon does a pretty good way of summing it up. So climate's what you expect. So right now it's winter in Oswego, a pretty northerly latitude. It's about 45, about halfway to the North Pole. We have a certain expectation of what winter in Oswego is like. That's climate. Weather is what we're happening to get right now. Some days it's really cold, and some days it's not. Some days it's snowing a lot, and some days it's not. Some days it gets abnormally hot, some days it gets abnormally cool. So like, for example, the recent cold in Texas, that's weather. That was a short-term event. It was terrible, and it lasted for about a week, but it was relatively short-term. That's weather. It's not related to climate. So there were a lot of posts about, oh, well, global warming can't be true because it's cold in Texas. It's not, first of all, it's not called Texas warming, it's called global warming. Second of all, that's confusing weather with climate. In many ways, a warming climate actually, probably, there's decent evidence for this, makes the gradient between the lower latitudes and the higher latitudes smaller. And so it's actually a little bit more likely that massive polar air escapes. That air is a little bit warmer than it used to be, but it's still a lot colder than Texas is used to. And so there's a lot of weird paradoxical ways that a warming world makes cold snaps, in some cases, more harsh, maybe not necessarily more likely or more frequent, but more harsh. And we're seeing that effect now. But again, we don't want to tie up too much between weather and climate. It's kind of a probability thing. If you want to be very ignorant about it, though, like, for example, Senator James Inhofe brought a snowball onto the floor of the Senate and said, it's cold out in Washington. I think it was right around Valentine's Day, so it was like February. It's cold out in Washington, D.C. It's snowing, therefore climate change isn't real. That was weather, that wasn't climate. And so another way of thinking about it is weather tells you what to wear each day, and climate tells you what types of clothes you have in your closet. When I lived in Texas, my closet looked a lot different than it does now, because the climate, the expected long-term weather patterns are much different in Texas than they are in New York. So that's weather versus climate. Another confusion that a lot of people have is that they say that climate has always changed it's going to continue to change, and we don't have anything to do with it. We're so small and insignificant that how could we possibly impact the weather? Well, the first 2 points are true. Climate has always changed, and it will continue to change. Another thing is that the Earth has been much hotter in the past. It's much hotter than it is now. It has been much hotter than it is now. It's also been a bit cooler, but in the grand scheme of things, in geologic time, so this graph here shows average global temperature in degrees Celsius. We're at about 15-ish or so now. The blue here at the bottom is Icehouse conditions. So large ice sheets are present. And then up here is hothouse conditions where they're not present. So right now we still have an ice sheet on Antarctica. We still have an ice sheet in the Arctic, Greenland. We probably won't for very much longer, but technically we're still in an ice house. The globe is warming. We're coming out of an ice age. The temperatures, the climate has been much warmer in the geologic past. So the big concern with global warming isn't that it's going to get hotter than it ever has. We're probably eventually trending that direction, but that's not the big concern. Temperatures, again, have fluctuated through time. The problem that we see here is that, for example, here's the Canberra Ordovician hothouse, very hot, maybe not the hottest on Earth, but pretty close. And then there's this big sudden slide into an icehouse condition. This sudden change corresponds with a big mass extinction. And so this is a cooling that causes a mass extinction. So cooling can be bad too. Warming is not inherently bad because we start warming out of that mass extinction and we start diversifying into another hothouse. Everything's pretty fine, and then we slide off another cooling, another mass extinction. So 2 of the first mass extinctions in the history of the Earth were probably caused by cooling. This very rapid change at the end of the Permian, which caused the Great Dying, was the first one that was definitively or related to a warm period, so warm bad too. It's really not about the magnitude, and it's not about whether it's hot or cold. It's about how fast things are changing. The magnitude swings can be large, but if they're slow over time, organisms have time to adapt. If a change happens over millions of years, evolution has time to work. Natural selection has time to work. Species have time to evolve to fit that new climate. If the change is very sudden, they don't. And so life might adapt to slow changes. They at least have a chance to adapt to slow changes. But when the rate is quick, that's the problem. And that's what we're experiencing now. The problem isn't that it's the hottest it's ever been, because it's not. The problem isn't that changes are unprecedented. The climate has always changed. The problem is the rate. The rate that is changing is the problem. So let's take a look at the Cenozoic. So this is the rest of geologic time. I've highlighted the Mesozoic here. They sort of start zooming in a little bit. You can see the scale changes, gets a little time in, but this is the Holocene, which is the epoch that we're in now. And this is where humans developed. All that we know of like written recorded history and agricultural, what we would refer to as civilization and society, occurred during the Holocene. And what you see is that through geologic time, these temperatures have been up and down, up and down, up and down, up and down. The Holocene is kind of remarkably stable, sort of oddly stable. And all of our recorded history developed during that time when temperatures were, pretty good for us. And that lasted for about the last 12,000 years. And now we're starting to see a sudden uptick. Again, it's not the fact that the globe's getting warmer that's the problem. Ice ages have caused mass extinctions as well. I don't think anyone wants another mile or 2 thick of ice above our heads here in Oswego. We don't want that. In many ways, warming is good. It'll avoid a next ice age. However, it's how fast it's getting warm. So changes in CO2 levels that are driving temperatures to change are changing in decades, levels that used to take millennia. So it used to take thousands of years to see the kinds of changes that we're seeing in decades. That's the problem. That's the problem with climate change, is the rate. It's changing quickly. Organisms can't adapt quickly. Society, it's arguable about whether society can adapt quickly. History sort of points to no, but the problem's the rate, not the magnitude. So keep that in mind. So how the hell do we know? How do we know any of this? How do we know what the weather was like 400 million years ago? 252 million years ago? How do we know anything about the climate? Did I say weather? I should have said climate. How do we know anything about the climate way back when? But nobody was there to see it. There were no thermometers. There were no weather stations. How do we know anything? Well, we use paleoclimatology. So paleoclimatology is paleontology, study of ancient life, paleoclimatology, study of ancient climates. So it's basically fossilized weather, really fossilized climate. I should probably change that. Really, when we're talking about climate, we're mostly talking about temperature and humidity. Those are the two factors that really matter, because those are the things that drive ecology, what lives where. So like think about temperature and humidity, like the difference between a desert and a rainforest. One's hot and dry, one's warm and wet. The temperature and humidity is what really matters. The organisms in one environment are radically different from the organisms in that other environment because the temperature and humidity are different. The expected long range, long-term climate of those two environments is different. And so the cryosphere, all the ice on Earth, the hydrosphere, all the water on Earth, the lithosphere, all the rocks on Earth, and the biosphere, all the life on Earth, they all respond to and they react to and they record trends in the atmosphere. So if the atmosphere gets warmer or drier, that's recorded in the rocks. That's recorded in the organisms that are recorded in the fossils that are recorded in the rocks. And so there's ways that we can read the rock record. Again, reading the pages, every layer of those rocks is a page in the book of life, in the book of the history of our planet. And if we know what to look for, we can decode that. And so I'm going to show you some of the ways that we do that. But a good example here is that the Sahara Desert, one of the driest places on Earth, one of the most inhospitable places on Earth, when human civilization was first getting rolling, it was radically different. You see on the map here, it's green. It was a lush, vibrant, temperate environment. And then over thousands of years, that changed. Humans were able to adapt by kind of migrating out, but we still see the historical evidence of these different migrations that were caused by the climate change. And eventually people started kind of settling along the Nile as like this little tiny string of habitable and otherwise inhospitable environment. It really drove the migration of human civilization, these changes in weather. So again, how do we know? We don't have direct measurements. So going back in time, we do not have direct measurements of temperature. We do not have direct measurements of humidity, but there are things that we know how they respond to temperature and humidity. So the one that people are probably most familiar with is tree rings. So tree rings in warm, wet seasons, they'll grow more, and so the tree rings will be wider. And in harsher climate, harsher times, the tree rings will be narrower. They grow less. And so if you core a tree or slab a tree to look at the rings, you can count them to see the years. You can see the seasons passing in the different colors. You can also see times when it was better for the tree and times where it was worse for the tree. In some cases, you can see the times when another tree grew up to block the shadow, and maybe you can, or block the sun, and you can see when that other tree fell down as this new tree starts expanding a little bit more. So you can read a lot from tree rings. Pollen is a good one. Different plants grow in different environments. If you start moving away from a forest to more of a grassland, less tree pollen, more grass pollen, you're probably getting a little drier. We can look at ice cores. In some cases, ice cores actually have little bubbles of atmosphere actually preserved. So little time capsules of ancient atmosphere that we can actually directly measure. Lake sediments, we can core with boreholes. Corals have like coral rings, in much the same way that tree rings do. Same thing with cave speleothems, stalactites, stalagmites. When it's a little bit wetter, they grow a little bit faster. When it's drier and there's no water dripping down carrying dissolved calcium carbonate, they stop. If they're flooded entirely, they also stop. So you can read that as well. All of these different things are paleoclimate proxies. They're not direct measurements, but we know the relationship. We understand that relationship and we can use it to reconstruct the past. One of the more quantitative ways of doing it is with stable isotopes. I'm going to walk through some details here, and I don't expect you to remember the details of how this works, but I would like you to know that stable isotopes of carbon and oxygen are used to reconstruct ancient climates. So what an isotope is an isotope is a molecule that has more neutrons than normal. So O16 is kind of the standard oxygen atom. O18 has 2 extra neutrons. It weighs a little bit more. It's a little bit heavier. Carbon 12 is kind of the typical. Carbon 13 has an extra neutron. It's a little bit heavier. So in different processes, these heavier atoms get filtered out, heavier molecules get filtered out, and the lighter ones get encompassed kind of more. So for example, if I have the oceans, the ocean has a set amount of O18 and O16, and that kind of varies with time, but there's a ratio. As water evaporates, the heavier stuff tends to get left behind, and because it's heavier, it's less likely to evaporate. And so clouds have more of the lighter O16, which means that when they rain, rain has more of the lighter O16. And so when we, and also when it snows and gets locked up into ice, that light O16 gets stuck in glaciers. And so when it's stuck in glaciers on land, it's not in the oceans. And so if we have higher oceanic values of O18, where a lot of O16 is missing, locked up in glaciers, we know that it was cold. Kind of similarly, but the opposite pattern is that when it's warm, trees produce more biomass. And as trees are performing photosynthesis, C12 is preferentially locked up over C13. The heavier C13 is left out. And so when there's more carbon activity, when there's more photosynthesis, we'll get higher, heavier values because there's more left. When the ocean's lower in the heavier stuff, that means there's less locked in the vegetation, which again means it's cooler. So it's kind of the opposite. But basically what we can do here is we can see that, really high oxygen 18 levels in the ocean, which are then recorded in rocks like calcium carbonates, like limestones. When they're high, it was warmer. When they're low, or sorry, when it's high, it was colder. When they're low, it was warmer. Vice versa for carbon. When oceanic C13 values are lower, it means that it was colder. And when they're higher, it means that it was warmer. And so we know this relationship. We observe it directly today, and we can see it in the rock record, and we can read those pages of the rock record. We can look at the chemical composition of a limestone layer, or we can look at the chemical composition of a shell that was built with calcite, CaCO3. Another thing we can use is strontium. So isotopes of strontium occur differently in rocks of the crust and in the rocks of the mantle. And so in times when there's more erosion of continents, which probably means that it's kind of warmer and wetter, the strontium ratios change, versus when it's probably drier and less colder and drier. And so over time, we see these swings in the strontium ratios, and it's sort of a proxy for the weathering rate. And again, we know that relationship between the weathering rate and the climate, and so we can use strontium as well. Again, I don't really necessarily care that you remember the details here. just know that carbon isotopes, oxygen isotopes, and strontium isotopes can be used to reconstruct the past. They are paleothermometers. They are climate proxy data. They're not direct measurements of the climate, but we know how they respond to climate. And so again, present is the key to the past. If we know how this stuff works in the present, we infer that it was working that same way in the past. We know the patterns, we can make predictions, and then we can test our predictions. Another thing that's good, so that's kind of the climate spiel. Let's talk about the plates. So how were the continents arranged? So remember that plates are actively moving around at about the rate that your fingernails or your hair grows, kind of on the slower levels of like 1 to 10 centimeters per year. That's about fingernail growth rate. That's like how fast the Atlantic is opening up. 30 centimeters is a little bit faster. That's about how your hair grows, or at least how your hair used to grow. That's where really kind of faster rate, kind of more like the Pacific. So this is a loop, and it starts at about 350 million years ago, at the end of the Paleozoic, right here with Pangaea. And you see over time those continents move apart, they split apart, and we start seeing things that look more and more like the present day. You see that little splash of white that jumps in there at the end. That's the big Laurentide ice sheet, the last glacial, quote unquote, ice age. But we see how much the continents change over time. And remember that dinosaurs are present throughout a good portion of this animation. We talked a little bit about allopatric speciation, how different species can arise as they're separated into different environments, into different continents. This is kind of how it happens. We see over time that what was once one solid continent of Pangaea splits off into several fragments. We see at one point that there's a large inland sea that divides North America from East Appalachia and Laramidia in the west. Dinosaurs were present at that time, and that seaway provided a natural geographic barrier for them moving back and forth. Populations on one side and populations on the other could not interbreed, and the environments were different, and they responded differently to their different environments. Okay, so plate tectonic motion, what's driving that? We already talked about this a little bit. Just remember that all of that movement of those plates is ultimately driven by these convection cells. Warm stuff heats up, it rises, it pulls the plates apart, and then it cools and it sinks. Hot heats up, it rises, pulls the plates apart, it cools, it sinks, you get subduction. So there's ridge push, where the ridges are being pushed apart, and there's slab pull, where the weight of the slab is sort of pulling down. And this is what drives that movement. This is what drives plate tectonics. It's active today. The plates are actively moving today. We can calculate now with GPS which direction they're moving and how fast they're moving, and we can use that to reconstruct the past. And so over time, we see repeated this Wilson cycle or supercontinent cycle, where we go from a solid continent, like say Pangaea, a supercontinent, we start splitting it apart, like East Africa today. That part of Africa is splitting off of Africa and will soon be its separate piece. Somalia is going to the east. It opens up enough to connect to the sea, like the modern Red Sea. That's a little juvenile ocean. It continues opening up, and it'll form a solid ocean like the Atlantic. Eventually, the ocean gets so wide that the rocks at the edge are very far away. They're old and cold and dense, and they start breaking off, start subducting, and the ocean starts closing, which is like the modern Pacific, where we have the ring of fire all the way around as the Pacific is being consumed and shrinking. Then you have terminal, where the sea is almost closed. Like, for example, the Mediterranean. Mediterranean used to be much wider than it is today. Eventually, Africa and Europe are going to solidly collide into each other, just like India has with Asia. And that's the final stage, is the suturing, where they actually fully collide. And then we have another supercontinent. This whole cycle takes about 250 to 300-ish million years. Pangaea was not the first supercontinent. and it will not be the last supercontinent. We've already named the next one, called Pangaea Ultima, probably going to happen when the Pacific closes and everything meets on the other side, but potentially the Atlantic could close as well. We'll see. But so that's the Wilson cycle there. So let's take a look at what the Mesozoic world looks like. So when we start things off in the Triassic, the first part of the Mesozoic, Pangaea is fully assembled. We see here this big mountain range. That's what's the modern Appalachians in North America, the modern Caledonides in Europe, the modern Atlas Mountains in Africa. This was all one continuous mountain range that formed when these continents smashed into each other to form Pangaea. At the beginning of the Triassic, right when dinosaurs and early dinosaurs first started coming on the scene, Pangaea was assembled, but you see here it's starting already to rift apart. So very early in the Mesozoic, Pangaea starts pulling apart. And what we see is that on the western side of North America, so this yellow star is us, we are here, this is us, we go. There's the Appalachians, eastern North America. Here's western North America. We see these off-board island arcs here that are kind of smashing in. Those are the roots of the Sierra Nevada mountains, so the early proto-Sierra Nevadas. The Rocky Mountains aren't a thing yet. We'll see how they develop in just a bit, but the plates are shifting around, changing in time. What we see here again, there's like areas of green, there's areas of brown. Again, Pangaea, one massive continent. The interior is very far away from the oceans, very dry. The early Triassic is a time of a lot of dry climate. And over time, as there's more and more splitting and more rifting, more and more ocean, it gets a little bit wetter, a little bit more humid. And of course, that drives changes in the environment, which then drives changes in the organisms, such as dinosaurs. So this is the next stage here is the Sonoma Orogeny. So again, this is when those island arcs here that were off board of Western United States, what eventually becomes the United States, these little island arcs out here start colliding in with the West Coast and warping things up in the mountains. There's a lot of active volcanism, relatively localized just to Nevada. And then conversely, on the east side, we're starting to pull things apart. What was the Appalachian Mountains, where those continents smashed together, there's that old existing weakness, that old seam. The continents start splitting apart then, not directly at that seam, but very close to it. And so the next thing that happens is the rifting. So, don't worry about remembering the names here, like Sonoma Orogeny or Newark Group. Just remember the general concepts here. So as Pangaea is tearing apart now, as Pangaea is starting to rift apart, there's these basins that form, these dropped down basins. So think about like taking a candy bar and stretching it apart. You'll see pieces kind of fall down and stretch and thin. You're stretching the crust, you're making a basin, a low spot. And in southern New York, along this area here, extreme southern New York, there's this Newark Basin, which are these terrestrial red beds, these land deposits. And we see dinosaur feet in there, the classic kind of three-toed dinosaur foot. Coelophysis here, this guy, is New York State's dinosaur. It's the only real evidence of a New York State dinosaur are the Coelophysis feet. You can actually go see some down in New York and mostly into like Connecticut and in New Jersey. But at this point, the rift is opening. The rift doesn't open here. This is a failed arm of the rift, but farther to the east, the Atlantic Ocean starts opening up. It's a little baby ocean. Some evidence of that is that there is all along the chain of the Appalachians, there is a lot of volcanism that dates to this time period, about 190-ish, 200-ish million years ago. And there's these dike swarms, these volcanic intrusions into the pre-existing rocks. And we also see evidence for these really large lava flows or sills of lava. So for example, the Hudson River Palisades. If you're from downstate, you've probably seen these, you've driven past them a bunch. This large cliff of black rock, this is a magmatic intrusion. It's chilled on both sides. It was intruded in. It's a sill. Don't need to know what a dike or a sill is or different. That's geology terms. But just know that the Palisades is evidence of volcanic intrusion that's recording North America splitting off from Africa. Pangaea is splitting apart. So by the time that we get into the Jurassic, we see that this crack kind of goes all the way through. We've fully progressed from the rifting stage where things are starting to break apart to the drifting phase where the continents are now just drifting away and the ocean's going to get wider and wider and wider. The Atlantic is born and it continues to widen to this day. There's a little bit of evidence that it's starting to be about as wide as it's going to get. Subduction may be initiating on the European coastline or just off the European coastline. The Atlantic might be almost ready to go into decline. But again, what we see here is tectonics, the plates moving around. Remember, there's stuff smashing in over here, mountains being built. Downwind of those mountains is a desert. It's called a rain shadow. Warm, wet air comes off of the oceans. It hits the mountains and it has to rise up. And it cools and it condenses and it rains out all the water that it has. And on the other side of the mountains, it's very dry. We see that in North America here, where along the Cascades and the coastal range, very wet climate. And then once you get inland a little bit further, very dry, very deserty. It's a rain shadow. We see that in the geologic past as well. You see a similar thing happening down here in Gondwana, the southern part of the supercontinent. So remember that tectonics, mountain range building, affects climate. It affects the weather, and that affects life. And then these things are also splitting apart and moving, and that affects the life. These things are all interrelated with each other. Climate, tectonics, evolution, they're all tied together, they're all linked, and they all respond to changes. Moving a little further along into the Cretaceous now. So we've talked about Triassic, we've talked about Jurassic. Now we're into the Cretaceous, getting towards the end of the Mesozoic, getting into the real heyday of the dinosaurs. At this point, there's actually a shallow inland sea here, covers most of the interior of North America. And in fact, it actually splits the landmass into two. Over here, we have Laramide in the west, and we have Appalachia in the east. What we'll see later on in the course is that this geographic barrier, this seaway, stops dinosaur populations from mixing across it, and Laramidian dinosaurs become very different from Appalachian dinosaurs. One thing that's sort of unfortunate is that glaciation has removed most of the Mesozoic rocks. So if you look at the map behind me, most of these rocks here are Paleozoic, the stuff that we talked about last time, the stuff that's older than the dinosaurs. Only when you go out west do you get into the major Mesozoic stuff. There is isolated Mesozoic. Again, we have Coelophysis footprints in New York, Connecticut, but they're small and they're far between. We know a lot more about Laramidian dinosaurs than we do about Appalachian dinosaurs, but we're learning more all the time. Again, it's very warm, warmer than it is today. Shallow tropical sea, lots of reef development, lots of carbonates, lots of limestones. One thing that's sort of interesting though is that the Cretaceous reefs are dominated by these weird rudist bivalves. They kind of look like little trash cans. So bivalves are things like clams that have two shells. This is a bivalve that has kind of a lid like a trash can. They don't make it through to the modern, and then corals kind of take over from there. So just an interesting side note, reefs have kind of always been a thing since like way back into like the Ordovician. But who's building the reefs and the dominant organisms changes through time, and across mass extinctions, sometimes there's dramatic changes. Then we get into Laramide Orogeny in the late Cretaceous. There's an ocean plate subducting here beneath the west coast of North America. It's subducting at a relatively shallow angle. Normally, when we think about subduction, we think about the plate going down very steep, magma coming up, and we get an ocean trench like the Mariana Trench, the deepest place in the oceans. That's because the plate is subducting and making that trench. Or we associate it with coastal volcanic chain like the Andes, so the entire west coast of South America, the ocean plate's subducting below, it melts, and you get that string of volcanoes like the Andes. In this case, though, the deformation and the volcanism are much more inland than you would expect. You see that the Rockies are pretty far away from the modern coastline. Wasn't quite that far away back in the day. We'll talk a little bit about that later. But really, it was more buckling and folding and less magmatism, and we made the Rockies. So this is the birth of the Rocky Mountains. You see this kind of low-lying area in here. That's the basin, the West Cretaceous interior seaway. If we look at the Appalachian Mountains, you can literally see where the Earth is folded and buckled from those continents smashing into each other. You can see it pretty well on this map here too, all the buckles and folds, just like pushing a rug across a waxed floor. These are the remnants from when we smashed in, made Pangaea. The Appalachians have been eroding for about 300 million years. The Rockies less so. That's why the Rockies are steeper, they're pointier, they're just younger. And so the Appalachians have been kind of eroding away, and eventually they'll be gone. The Himalayas are the largest mountains on Earth right now. Eventually they'll be eroded away to nothing, as the Appalachians are sort of doing today, very slowly. So by the time we get to the end of the Mesozoic, when the Chicxulub impact actually occurs, we'll talk about that more, but Chicxulub actually impacts right here at about 66 million years off the Yucatan Peninsula. By the end of the Mesozoic, things look pretty much like they do today, although there are some pretty big differences. We can see North America, we can make out the Atlantic, we can make out the South Atlantic, we can see South America. There is no Central America yet. That'll be formed later. Africa is now free floating. Australia is still hooked on to Antarctica, very southerly, polar. There's dinosaurs down here. Let's talk about what they're like throughout the course. India hasn't yet smashed into Asia. It's going to continue moving north. And you see that Europe's kind of this dotted landscape of tiny, almost like islands that are separated. Can dinosaurs migrate across from North America through to Asia and kind of island hop across? Let's discuss that later on. So that's all I've got for today. I hope you enjoyed that. And we'll talk more about the life that was during the Mesozoic next week. So goodbye.